Alright, the purpose of this part of our lecture series is to discuss Le Chatelier's principle, which is based on the law of mass action and basically talks about how systems that are at equilibrium move to reduce stress that has been applied to the system. So if I make changes in the system will move to reduce that by either producing more product or more reactant or whatever's necessary to offset that change. And so the first thing we want to look at then is how changes in concentration of products and reactants affect the system. So let's take a simple example here with the Haber process where I have nitrogen and hydrogen reacting to make ammonia. All in the gas phase, it establishes an equilibrium. Let's say that I add some ammonia to this mixture after it's equilibrated. So I've stressed the system. I've added extra product. Essentially, I have made Q larger than K. And so in order to relieve some of that stress, we're going to convert some of that ammonia back to nitrogen and hydrogen in order to relieve the stress on the system. And so you can see from our diagram over here that initially we are starting out with everything at equilibrium. We're going to spike ammonia, and as we initially spike it, it rises and then it starts to fall. As it falls, hydrogen and nitrogen are being produced to relieve that stress. Some things to note: the ammonia does not fall back to its original position, nor does the nitrogen and hydrogen remain at their initial positions. They all shift a little bit to reestablish the value of K, but since we have more mass or more moles of stuff in the system, they'll all end at higher values. Only ammonia will rise first and then decrease, while nitrogen and hydrogen simply rise. So anytime I add products to um, a system that's at equilibrium, we're going to shift to the left to produce reactants. And if I add reactants, then we'll shift to the right to produce products. Conversely, if I remove products, then I will shift to the right to replace them. And if I remove reactants, I'll shift to the left to replace those. So again, it's all about relieving stress that's applied to a system. So other things that we can change volume and pressure. And what we need to remember about this is that volume and pressure are not directly related, they're inversely related when temperature is constant. So that when a volume gets small, the pressure gets high. So we always want to be moving to reduce stress that we place on a system. And so if I decrease the volume of a system, essentially I make the partial pressures of all the gases in that system higher. Or if you want to think of it concentration wise, I make their molarities higher because I have the same moles in a smaller volume. So this will always shift to the side of the reaction with fewer moles of gas. Since all these pressures are higher, to relieve the stress, we want to get back to a point of as low pressure as possible. Now, are we going to be able to get to a point where we're back to the same pressure? Probably not, but we'll move to lower that increased pressure within the system. So we'll always shift to the side with fewer moles of gas, because if you remember what causes pressure, it's collisions of gas molecules with a container. So if I lower the number of molecules, I lower the number of collisions. Something that's also important to note here is that if I have an equal number of moles of gas on each side, then I can decrease the volume all I want, and I won't affect the equilibrium position of anything. It has to be a situation where there are more moles on one side of gas on one side of the equation than the other. Then we can see an effect from changing the volume. So if I increase the volume, so I stretch out my container, essentially the molecules hit the walls less often and the pressure has dropped. So my stressor is a reduce in pressure. So in order to remedy that stress placed on the system, as long as again I have different molecules, number of gas molecules on both sides of the equation, my system will shift such that it will produce more gas molecules to make up for the pressure that was lost when the volume was increased. Again, if we are in a system where we have equal gas moles on either side, then this will have no effect. It's also important to note that I can add any species of gas I want that's not involved in the reaction and won't interact with either of the reactants in a side reaction, and it will not change the equilibrium whatsoever. Will it change the total pressure inside the system? Yes. Does it change the partial pressure of either of the gases in the system? No. And so there's no gain to be made by shifting the molecules around. So also we need to note that I can have the equilibrium position affected by pressure and volume, but I cannot alter the value of KEQ by changing pressure and volume. The equilibrium constant value is directly tied to the temperature. So long as the temperature stays the same, the equilibrium constant value should remain the same. The next thing we can do is look at how temperature does affect that. We've said that it does, so now let's take a look at how it actually does that. So we have two ideas that we can have for reactions. We can have endothermic reactions, which require heat and take them in from their surroundings, or we can have exothermic reactions that liberate heat to the surroundings. So essentially, I can look at endothermic reactions using heat as a reactant and exothermic reactions producing heat as a product. So if I add heat to a system, essentially that would be like a stressor. That's like adding a product or reactant. And so what the system will do is it will use the potential energy stored in its reactant and product bonds to try to offset the heat that I add. So if I add heat to an endothermic reaction, it's going to use that to fuel the reaction and produce more product. If I add it to an exothermic reaction, it's going to slow that reaction down. To get rid of the extra heat, it's going to have to bind it back into reactant molecules and store it in potential energy of bonds. And so what we're going to see then is this is going to change the value of the equilibrium constant. It's going to change the moles of product and reactant formed, but it's not going to be reflected in KEQ. Everything up to this point, when it changed them, like the volume, it changed both of them, and they were both in KEQ, so we could see them offsetting each other, and so KEQ stayed the same. However, in this case, we're just going to see the change in the concentrations, and we're not going to see that reflected in KEQ. So essentially, since KEQ is based on mass action, energy is not mass. So if that helps you remember it, it doesn't apply to that. So for an endothermic process, if I raise the temperature, I'm going to increase K. That means I'm going to produce more product, and so the value of K will get larger. The converse is also true. If I am going to lower the temperature, then I'll decrease K. Lowering the temperature will cause more products to be or reactants to be made, and K will go down. For an exothermic process, if I raise the temperature, my K value will drop. In this case, it's like adding a product. I'm adding extra heat. I have to do something with it, so I have to bind it back up into my reactant molecules. And also, the converse to that is true. If I decrease the temperature of an exothermic reaction, I'm going to speed that reaction up. Decreasing it wants to replace the heat that's being taken away, so it breaks product or reactant bonds to release the energy that's stored in them out into the exothermic process so that it can replace the heat that has been taken away. Last but not least, Le Chatelier's principle, we can see how it is applied to a catalyst. So if I add a catalyst to a reaction, remember what a catalyst does is provide alternative pathway. Usually this alternative pathway, they're calling it activation energy and activation energy prime. Usually that alternative pathway provides a lower activation energy for the reaction. This can be through just changing one step, or it can change several steps where the sums of those steps are still less than the overall activation energy for the first process. But essentially, we're going to lower the energy required to get started. So this does not change K because it doesn't shift the position of equilibrium in a system. Essentially, delta H stays the same. And so it's not going to make me make any more or less. It's just going to provide me an alternative way to get there. And so the alternative way, because the activation energy is lower, it tends to be faster. So do I get to equilibrium faster? Yes. Do I change how much product I make? No. And in order to change K, I would have to shift how much product was made. So the reason this happens is that a catalyst, while it does lower the activation energy for the forward process, it's important to note that if we think of going back the other way, if I lower the hill going one way, note here, lowered the hill going this way, it also lowers the hill going in reverse. And so that is accounted for in both the forward and reverse reactions. That's why we reach equilibrium sooner. So it does not change the equilibrium constant or shift equilibrium position ever. The only thing that ever changes the equilibrium constant or shifts the equilibrium position, things can shift the equilibrium position, but the only thing that will ever change the value of the equilibrium constant is temperature. And that can be applied to the following question. So we're going to take a look at the reaction of silicon dioxide, SiO2, with HF to make silicon tetrafluoride and water. So what we want to do then is note that we're doing this reaction above the boiling point of water, so we're very hot, and we want to predict the effect of the concentration of silicon tetrafluoride, a product, when we do the following things. So the first thing we want to do is remove H2O gas. And we need to note that H2O gas is a product. So I'm removing a product. So if I remove a product, I want to try and replace that. So essentially, I've made Q less than K. I've taken product away and made that fraction smaller. So if I stress the system by removing something on the right, then everything has to move to the right to replace it. So SiO2 and HF will react again to try and replace the water that we took. And as it's making more water, it will make more silicon tetrafluoride, and so that concentration will increase. If I add some liquid water, well, we have to again make note of what we know from the problem. We're above the boiling point of water, so if I add liquid water to this system, it's going to vaporize, and so it's going to produce H2O gas. And so because we are above the boiling temperature, we're going to add product. So when I add product, I've stacked on the right. The system wants to reduce that stress by moving back to the left. And so if I add extra water, I'm going to produce more silicon dioxide and more HF, and that's going to consume some of my SiF4. So essentially we've made Q too big by adding water, and so SiF4 will have to react with that extra water and decrease its concentration to relieve the stress in the system. In part 3, we're going to remove HF. Removing HF, that's a reactant, so we have made Q greater than K by removing reactant. We've taken something away from the left side, and so the whole reaction will shift to the left. And so as I try to reproduce HF to replace that what was taken, SiF4 has to react with H2O, and so that will bring down the concentration of SiF4 in the system. And then last but not least, we're going to remove sand. Sand is SiO2, silicon dioxide, and note that it's a solid. And also remember that solids don't appear in equilibrium constants because their concentration in themselves is a constant value. So anytime I remove a pure solid or a pure liquid from a system in equilibrium, it has absolutely no effect. As long as there is enough around to be in equilibrium, it has no effect. So we must add that caveat. It says some sand, not all sand is removed. So it's not going to affect it because it's not involved in the equilibrium constant. So very briefly, let's summarize what we know for Le Chatelier's principle. If I make changes in concentration, can it shift equilibrium? Yes. Can it change the equilibrium constant? No. If I make changes in pressure, can I shift equilibrium? Yes, I can. Pressure and concentration are related through a constant. Can it change equilibrium? No. Can changing the volume shift equilibrium? Yes, it can. We'll move to relieve that pressure by moving to sides that have more or less gas. Can it change the equilibrium constant? No. Can temperature shift equilibrium? Absolutely. Can temperature change the equilibrium constant? Yes, it can, because heat is not reflected in the equilibrium constant. Again, just to remind you, that will cause the value of K to change. And then can a catalyst shift equilibrium? No. Can it change the equilibrium constant? No. Catalyst has absolutely no effect other than making us reach that equilibrium position faster. So things to take away here. All changes except for catalyst will cause a shift in equilibrium, and no change except for a change in temperature can change the value of the equilibrium constant. And that is basically what we need to know about Le Chatelier's principle.